Well, hello again. I'm going to restart my timer. I've already attempted this once, and there we go. Starting my timer. So I'm going to try to keep these videos broken up into 15-minute blocks. I did that by accident initially when I started recording videos, just because of the technology I had at the time. We could only do 15-minute videos. And I found from student feedback over the years that that actually is a nice workable chunk to break content up into, that you can kind of take a break in between and you feel like you've accomplished something after you've gone through about 5 or 6 parts of a lecture at that point. As I mentioned, I've mentioned this on my Canvas course, but if you're joining us from the outside world, um, you won't see a lot of me uh, as I record these videos. I'm going to try to replicate what I do in the classroom. And what I would strongly urge you to do is treat it just like you were sitting in the classroom with me. I've got 20 years of experience teaching engineering students at this point, and I interact with students that have graduated and gone on in the workforce and very successful. I'm very comfortable what I do. Um, so what I wanted to do was replicate what I'm very comfortable doing in the classroom because I feel like from feedback is it's very effective. So treat it just like you're in the classroom with me. Take notes, work through the problems with me. Double check my numbers because if you look at some of my older videos, you'll sometimes see I'll get some things wrong from time to time. And so you can write in the comments that if you think there's something you have a better suggestion, and we can have a conversation. Okay, these are all fine. Um, So at any rate, let's get going, shall we? There's gonna be more that we'll talk about as we go. If you look on my YouTube channel, you might still find the older version of these videos. I was watching those just a little bit ago, and I feel like they're very, very good. But I do have some newer technology here, and I know the audio is going to be much better on these. Hopefully, the content's as good. If I feel like it's as good, I probably will phase out those older videos. But I might also hit a point where I'm like, I'm not really adding any value doing it this way, and we just refer back to the older ones. But we're going to try it this way for now. Okay. So here's what we're going to do. We're going to talk about thermodynamics and obligatory kind of starting out. We define the two Greek words that define thermodynamics or thermodynamics originates from. There's a Greek word, thermi, which refers to heat, essentially heat energy. So thermodynamics deals with energy. It is the study of energy, but we're really going to focus on heat energy. Whereas in a Physics 1 class, which you should have already had a calculus-based Physics 1 class before being here, in a Physics 1 class, we would have introduced conservation of mechanical energy and then maybe mentioned a little bit about other types of energy. Here, our focus is going to be on utilizing heat energy because that's the whole study of thermodynamics is it's a combination of thermi, which means heat, and a Greek word, as best I can tell, dynamikos. Loosely, dynamikos refers to power, motion. Now, you're going to notice very quickly my handwriting is not very good. I'm actually trying, if I'm being honest with you. I'll do my best. So, thermodynamicos, the whole science of thermodynamics was born out of a time when we had just introduced the idea of a steam engine, this object that revolutionized our society as a whole. It brought about the Industrial Revolution. The idea is you got this box that inside this box is basically kind of a piston, and that piston then is attached to some sort of a drive shaft that hooks up to a wheel, right? And that piston can basically, by adding, and sometimes my drawings are a little better than this. This is kind of a half-baked idea. I just thought I would draw up. If I add a bunch of heat, right? I add a bunch of heat to this thing. Heat. What happens to a gas when you heat it up? It wants to expand, right? So it's going to drive this piston to move. So I pour a bunch of heat energy into this thing. It causes this piston to move, and you hook this up to a wheel, and it's going to cause this wheel to spin. Thermodynamics means I'm going to take heat and I'm going to turn it into motion. I went out and Google searched um, steam engine GIF images, and this one I can't find a good source, reliable source on this to reference it back, but you can see how I got to it. I just went to Google and typed in, hey, show me some steam engine GIFs. This was about halfway down. This one, I really like this one. This one shows kind of a more modernized version of this, but you see up top here, oh, well, okay. Didn't intend to do that, but you see up top here, you've got this rocker going back and forth that's directing hot steam in one side, causing expansion, and then it's going to come over here, and now it's going to push hot steam in the other side, causing expansion, and that's going to push this cool steam back out to an outlet, in and out, in and out. This is the whole foundation of thermodynamics. Add heat in, get heat to generate motion, to extract power. That's it. Now, it's going to get a lot more complicated and a lot more intricate than that, but that's the whole basic idea. So there are two things that drive this. One is the first law of thermodynamics. The first law of thermodynamics essentially says that if I consider the rate E dot n, that's E with the dot above it, that means the rate at which heat energy comes into a system, and subtract out the rate at which energy goes out of a system, that's going to equal the change in the energy of our system with respect to time. And the way I always like to say this is a conservation law. Conservation laws always take the form of in minus out equals change. In minus out equals change. So the rate at which I put energy in minus the rate at which energy goes out is equal to the rate of energy change for our system with respect to time. If you've not had fundamental single variable calculus, integrals, and derivatives, you're not ready for this material. You're welcome to hang out and learn, but if you're trying to take a Thermodynamics 1 course without Physics 1, or normally a lot of places Calc 2, that's single variable integrals, you're really going to struggle, if not fail here. So you've been warned. I'm going to assume you have that skill set on board and proceed accordingly. Conservation of energy is the first law of thermodynamics. It's going to take a much bigger, broader form than what you saw in Physics 1. We're going to expand on what you've already learned and move forward, be like good engineers. We're going to apply existing knowledge to solve problems. Later in the semester, we're going to talk about the second law of thermodynamics. Second law of thermodynamics deals with the quantity we call entropy. Second law of thermodynamics says that the change in entropy is always going to be greater than or equal to the amount of heat transfer divided by the temperature at which that heat transfer occurs. I always have a cup of water here. I get hoarse when I talk a lot if I don't stay hydrated. This water, I've pulled water out of my refrigerator. The refrigerator has cooled this water down, causing the molecules to be less entropic, less in what is entropy, right? What is entropy? If you don't know, maybe we mentioned that in a chemistry class. But if you don't know, go look that up. Pause here, go look up what is entropy, and then come back. I'm waiting for you to pause. Okay, you got it? Cool. Entropy, I'm hoping you found entropy is kind of chaos or disorder, right? So I mentioned my water here. If I pull this out of, if I put this in a refrigerator, that refrigerator is going to remove heat, going to pull heat out of it. By removing heat, those molecules will become less entropic, less chaotic, more predictable. If I heat this water up, as it's sitting out in my room right now, gathering heat from the outside area, it's heat's going into it. So as heat goes into it, The chaos or the unpredictability of these molecules are doing what? What's happening there as I add heat? They're becoming more chaotic, more unpredictable. So as I add heat, right, as I add heat um, to those molecules, right, positive Q means a positive change in entropy. So as I add heat, I'm going to increase the entropy. What we find is that this increase in entropy is always greater than the amount of entropy change caused by the heat divided by temperature quantity. Entropy is always being generated. At best, we conserve entropy. That's the limit there, the equal to sign. So at best, we put as much entropy into something as what we meant to. Right? All right, later in the semester, we don't have to worry too much about that right now. I'm going to ask you to pause here. Based on that, I want you to think about where have you used thermodynamics just today? Just come up with 3 places where you think you've used thermodynamics today based on what we just mentioned. This is the first law, energy N minus energy out equals change. And then the second law deals with what heat energy does. So come up with 3 examples where you've used thermo today. Go ahead and pause. I'm going to wait for you. All right, you got three things, 3 places you've used thermo today. Compare your list to mine. Here's guarantee 3 places you've used it today. Electricity is energy. Well, electricity is the movement of electrons. That doesn't happen spontaneously. It happens by driving. We often use magnetic fields to push them, but we basically rotate magnets or spin magnets around using power from an engine or a motor, and we push those electrons using magnetic fields. So we're converting. We're using like that steam engine I showed you guys a second ago, right? We use something like this. And over here on this output shaft, I use this to turn a generator and that moves electrons around. So we're transmitting energy by work, right? So electricity is the transmission of energy. Now we can easily turn that right back into heat by pushing it through resistors. Um, so anyway, you're sitting here watching me right now, an electronic device that's using energy that's being transmitted from somewhere and generating light and sound with that based on what your processor's telling it to do. Um, Depending on when and where you're watching this, you probably have some sort of heating going on. Um, or if, for us right now, this time of year where we're at, middle of America, in this early summer, my air conditioner's running. You can probably hear it running right now, right? Air conditioning and heat, these are moving energy around, right? I'm causing molecules to be more chaotic or less chaotic, depending on which direction I'm moving heat into or out of that air. Very important for us as humans. Um, One that we don't normally think about is the weather. Friend of mine is our meteorologist professor where I work, and um, he works part-time as a meteorologist for some of the news stations around here, and we have wonderful conversations about thermodynamics. We talk a very similar language. Now, for us, we're trying to extract power and make things move. They're talking about generating temperature and pressure gradients and what that does to the wind speed and the chaos in the environment, like tornadoes and hurricanes. Right, but that's all thermodynamics, right? So interesting places. I don't know if this list matches yours, but yeah, I'm betting you got some really good ideas there. Okay. Now, another place I want you to pause. So I'm going to ask you to pause probably a lot here in the first couple of lectures, a lot, because I'm really trying to get you to think about things. But I will ask you also sometimes to just pause or in between videos, I'll say, hey, go work this out and come back to the next video and have this ready. I want you to pause here and I want you to do a little research real quick. If you don't know the answer to this, and I'm almost to the end of this video, so it's actually going to work out really good. I want you to pause here. I want you to go learn about what is the difference between these 2 words. What is a dimension and what is a unit? Because these are not the same. They're very closely related. But these refer to 2 different concepts in engineering and science. So I want you to stop here. You don't even have to pause. We're just going to go to the next video. But before the next video loads, I want you to have an answer to this here. So between videos, go research. What is the difference between a dimension and a unit? I'm going to stop recording there.